apply a slider, the whole thing could slide up and down. So it's not fully constrained on the one end. And so for this slider here, we're simulating the fact that this thing can slide in one direction. Yeah, so it's this one right here, this front face, and then the two edges on either side. If I go back into Catia, it's right here. So you've got this longer one, this front one, this square flat one, and then this one right here. So we press OK. We've now got slider constraints applied. Okay. So in the specification tree, the slider should show up underneath the restraints. So I'm not seeing, there we go. So there's our restraints. So anytime I constrain something in a certain direction so that it won't move in that direction, it should show up underneath the restraints. You can double click on it and you can go in and edit it if you need to. So if there's something that you accidentally constrained that you didn't want to be constrained, you can modify that. So that's how you apply constraints. Again, I could have used a clamp to cantilever it at one end if I wanted to. There's a whole variety of different types of constraints. There's a sliding pivot, so it'll slide up to a point and pivot. There's a ball joint, so if you trying to do an analysis on like a trailer hitch and it's sitting on a ball joint, you can simulate that. So yeah, there's a whole bunch of different types of constraints. So after we've applied our constraints, the next thing we need to do is we need to apply a load. So we'll go to the next section inside of our tutorial. So creating a distributed force load. So anytime you're inside of a finite element program, you'll need to kind of simulate real-world constraints. If something's connected to something else, you need to somehow simulate how that would react in real life using these different types of constraints. But then you need to apply a load. So if your race car, for example, we're looking at the bumper part maybe, there would be two constraints in there showing where the screws are holding the bumper in place, and then you'd need a load showing where the impact would occur. And then you can apply an actual value to that load to simulate how hard you're hitting something. So to apply a load, there's a distributed force button. The distributed force button is kind of a little curve here with some arrows on it. So if you come into Catia, there should be this one right here, distributed force. Sorry?
You don't have to make the loads active.
Say again?
It says you select loads and make it active. You have to make it active.
Yeah. So this task will show you how to distribute on a face of your part a resultant force. You'll select the loads object in the specification tree to make it active. Click distributed force on in the loads toolbar, and then the distributed thing will show up. So if we come in here, we'll click on our loads, and we'll click on the distributed force. And then if we come back to our tutorial, it says which directions we can apply our forces. So we're going to apply a negative 50 Newton value in the Z field. The resultant force vector norm field is automatically updated. And then we're going to select the part face as indicated below. So we're going to grab this face right here. So if we come in here, we'll rotate this a little bit here. The force we'll put is negative 50. So if we look at our datum up here in the corner, the Z direction, the positive Z direction is heading out this way, right, into our toolbar. So that the load we're going to put on it in the negative Z direction is going to be applying a force like in this direction. So we'll click on our face, and then there should be some arrows indicating that the load was applied, and then you press OK. So press OK, and now we've got a force. So there's going to be a force pushing down on this side right here. Okay? So similarly, if you want to apply other loads, there's a pressure load. So if you're ever doing an analysis where maybe you guys are fortunate enough to do some analyses on like submarines or something that has a lot of pressure applied to it. And you're inside Catia, you could apply a pressure onto a surface. There's an acceleration load, so if something's accelerating up to a point, you could do a line force density. You can do a temperature field. So if you ever take a class later on in your mechanical engineering careers, and you might do like a mechanics and materials course, you'll find that temperature will also affect how much things will deform, especially if you have multiple materials connected together. So you could do a temperature field to simulate how some ends of the part might be hotter than others, and you can see how that would deform. But for right now, we're just going to stick with some very simple models. We'll just stick with distributed force for impact. But again, all of these are available to learn inside of Catia. You can even do combined loads, so you can do multiple distributed loads and have them sum up. So once you got your constraints, then you'll need your loads. Once you're done with your loads, then you can compute a static case solution. Okay? So if we click on that, it's, again, here's the little help file for you. So if you click on the external storage, it's kind of like three little disks here with the red arrow. In the solver's toolbar, this external storage dialog box will appear. Basically, the external storage is just letting you select where you would like to save your results. Okay? So it'll have some results and some computation data, and you can kind of tell them where you would like to save that stuff. So like in your E drive or C drive or wherever, your J drive. Anyway, so that'll let you tell you where you'd like to save it off to. And then we can go ahead and compute our actual finite element analysis. So I'm not even going to bother with the external storage just because I don't care about saving this. But the solver or the computer is just a little calculator icon. So if we click on that, it'll say what would you like to compute. You could do the mesh. You could do the selection by restraint. I mean, you could break it down into different types of things. We'll just go ahead and do all. And so it'll take some time here. It'll go through each one of these. Rotate constraint. Yeah, this is not fully constrained. That's okay. Yes. Okay. So we've got our static case solution. And it should go through this. And then upon successful completion of the computation, the status of all objects in the analysis specification tree will be updated. So if this thing works, there shouldn't be the little swirly marks next to every little thing in the tree. So normally when you're inside of Catia and something's out of date, there will be a little swirly icon by something in your part tree that indicates that there needs to be some sort of update performed. Inside of Catia, when you finish your solver, all of those will go away, and that will indicate to you that it's solved. Okay? So now we need to be able to actually view our data. So that was the solver. So if we want to view displacements, there's a displacement icon that looks kind of like the state of Utah. It's got little kind of a rectangular shape going on there. Anyway, this will allow you to see the displacement, and when you do it, it will indicate a series of vectors. So it actually doesn't quite show the model right off the bat. So if you come in here and click on this, it'll show how this thing has displaced. The red indicates the most displacement. The blue indicates the least amount of displacement. So we can look at our model and say, hey, this makes sense. We constrained this end, so it didn't displace as much. We didn't constrain this end, and there was a force applied in the downward direction. And so we can tell that all of our displacement arrows are pointing in that direction, and most displacement occurred here at the end. So using just a little bit of common sense, we can look at this and say, hey, it looks like it worked okay. the accuracy of the actual results might not be correct depending on what numbers you put in and how you constrain it, things like that. But you can use a little bit of intuition to see if it generally looks like it solves correctly. So that's how you can do the displacement. If you want to take a look at the actual stresses in the part, there's this similar looking button here, but it's got kind of a rainbow inside of it. If you click on that, it'll show the actual displacement. Let's see here, hang on. Let's see, traditional displacement vector. Material options selected, okay. It's unusual, I've never actually seen it display like that. Yeah, I was going to say, I want to do something like that. With shading. Let's see, shading with edges. There we go. Material. There we go. Got it. Yeah, I was going to say my filter was on. Okay, so yeah, so you can see the areas of high stress. So there's a lot of stress right here, a lot of stress down here. So if you look at this part and you've done a finite element analysis on it, and you see that there's high areas of high stress, you can actually go back into the part and add some material to that portion of the part. And then when you come back into the analysis, it should update the part automatically because there's a direct link to it. So all you have to do is rerun your solution by hitting the compute button. And it will show the new stress values, and you can see if you can get those stress values to reduce. So you can make the part stronger. And then if you guys want to apply a label, there's a couple other tools here I'll show you real quick. But if you guys want to apply a label, like saying what the maximum and minimum values are, there's this image extrema button that you can click. So it looks similar to the von Mises button, just has an M next attached to it. And so that one is, let me see here, if I can remember it. I'm not seeing it here. Yeah, let me pull some of these out here. Oh, come on. It's being a pain. There we go, right there. Image extrema. So if you click on that, you can kind of pick your minimum extreme at most, maximum extreme at most. Let's see here. So 2 and 2 looks like. Hit OK. There we go. So that will tell you where the minimum stress is and the max stress is and what their associated values are. Okay? I'm sorry? So when I clicked on the image extrema, it says at most, like minimum extreme at most, I put in number 2. Because you need to actually have a value. So like the most deformation, you'll need to put in. Let's see here. It should say right here actually. To obtain local and global extrema values on the von Mises stress field magnitude. So you'll put in some different magnitudes for this. Anyway, there's a couple other cool buttons down here I wanted to show you guys. So there's a amplification magnitude button. So if you click on this thing, you can kind of see the amplitude of the stresses increasing.
Which tool did you click?
Yeah, it's this one right here. It's called amplification magnitude. So then you can change the scaling factor of your deformation and kind of see how it moves up and down. If you want to see an actual in motion, there's an animate button. So that will kind of show you the original and then show you how it deforms as the, let's take it up to like 50. Yeah, so you can actually see the deformation occurring as the load gets applied more and more up to its actual strength. It's